Okay, so we're going to do two optimization problems here to start out. These ones are are on the easier side. But the purpose here is the concept of these is the same. And this is how you do it. So optimizing, we're making things either the biggest possible or the smallest possible. So that's what we mean. So let's do this one. This is how we do these things. Read the problem, figure out what's being asked. So we're asked to find two positive numbers whose sum is 20 and whose product is maximized. Okay, so whatever it is you're asking to find the biggest or smallest of, that's what you need to get an equation for. Once we have that equation for that thing we're asked to find the biggest or smallest of, we take the derivative and set it to 0 and solve. Why? Well, think about what we did before. How do we find our maximum and minimum values of a function? You take the derivative and set it to 0, or see where find the critical numbers, where it's 0 or undefined. So that's the reason why we do that. So you got to find the sum is 20. So if we have our first number and our second number, well, we don't know what the first number is, some number x, but they have to add up to 20. So this has to be 20 minus x, because when I add these two, the x's add up to 0 and we get 20. So if this is 5, this is 15, and it's going to add up to 20. So there's our two numbers. Now, the product of these numbers is the biggest. So what is the product? It's x times 20 minus x. If we distribute, we get 20x minus x squared. So this is the product. Now we take the derivative and find the critical numbers. So the derivative is 20 minus 2x. When I set that to 0, when I add 2x to both sides, we get 2x equals 20. So we divide and we get x equals 10. So that means our first number is 10 and the second number is 20 minus 10, which is also 10. So notice 10 times 10 is 100. Now what if I picked, instead of 10, I picked 9? Well, we would have 9 and 11. Yeah, that adds up to 20, but 9 times 11 is 99. It's not quite as big as 100. So if you pick any other arrangement of numbers here whose sum is 20, when you multiply them, it's going to be less than 100. So that's how we do that. So let's do the next one. We want to find the smallest perimeter. Well, so we need an equation for the perimeter. We know the perimeter of a rectangle is twice the length plus twice the width. But we want this equation to be a function of just one variable, so we can take the derivative and solve. So that's what we got to take the derivative of, because that's what we're asked to find the smallest. But the area is 12 square feet. Well, we got to use that to make this a function of one variable. So the area is 12 square feet, but the area of a rectangle is length times width. So I can either solve this for L or W and plug it in here to make our perimeter equation a function of one variable. I'm going to solve for L. So when I divide by W, L is 12 over W. So when I substitute that, we get 2 times L, but L is 12 over W plus 2W. Rewriting, we get 24. Let me write this as W to the negative 1 plus 2W. Now we take the derivative. So the derivative of our perimeter is minus 24 W to the negative 2, or over W squared. And the derivative of 2W is 2. Now, one critical number is 0, because that's when our perimeter prime is undefined. So that is a critical number, but we can throw that away, right? Just think about it. Why don't we have to worry about the width being 0? Because if our width is 0, you don't have much of a rectangle, do we? Right? So sometimes you can just throw numbers out just by thinking of the practicality. Yeah. So when is this 0? Well, if I add 24 over w squared to both sides, we get 2 is equal to this. If I multiply by w squared, let me erase this side so I can. So when I multiply by w squared, we get 2w squared equals 24. And then we divide by 2, we get w squared is equal to 12. So w, when we take the square root of a square, we got to use a square root property. There's a positive and a negative square root of 12. Now you can't have a negative width. So again, we can throw the negative out. So the answer has to be the width is the square root of 12. Well, if the width is the square root of 12, then the length is 12 over the square root of 12. And those are the dimensions for our length and width to optimize, to get the smallest perimeter of this particular rectangle. Now, what is the smallest perimeter? I guess if we want to actually find the smallest perimeter, just plug in these 12 over root 12 for L and root 12 for W. That would actually be our answer for the smallest perimeter. But this is the answer for the dimensions.